Okay, see, today's lecture is going to cover what we call irregular sea waves. Some people call this actually also random. Now, see, yesterday we talked about regular sea waves, nice sine curves coming, but as you all know, if you really go to open ocean, you will never find a wave which is very nice and sinusoidal. You will find wave which will probably look something like that. If you try to monitor it at some location, it will look like that, or if you try to take a snapshot, also will look like that. It will not look like a nice and sine curve. In other words, what will you find is that there is a lot of irregularity. It does not at all look like a sine curve, or one can say it is random. In fact, one can show that if you keep taking for a long time, it seems to be a never repeating kind of a signal. As far as type of signal is concerned, it will never be exactly same. Okay, this is what we call obviously irregular waves. Irregular, the word irregular is more used by or coined by ship people, naval architecture background, but eventually when these offshore structures started coming up, more of civil engineering people were concerned. They started using the word random waves, which is both are same thing. So this words we will use it interchangeably. Irregular means random wave. Why we are going to need to study that? Because ultimately our aim is to find out when I am going to put my ship in a sea, a real sea, how the ship behaves. Now, a real sea is not composed of idealized single sine waves. It looks something like that. So, there is no point from, my ultimate aim would be not to figure out only how a ship behaves in a regular waves, but how it is behaving in this wave. So, I need a description of this wave. That is a very critical thing, because I must describe what is my environment in which I am going to put. Just like yesterday we talked about one single wave which is environment, but the real environment is irregular waves. So, we are going to talk about this. Now, let us see how we can go about it. Let me give an example. Supposing you monitor wave at some location, you may find it goes like that irregularly. Okay. Now, what happens is that here we first of all we have to define, because it is a random signal, we must define certain parameters by which you may say this curve is characterized. Let us say that this is plotted against t at some location at some given x at a given location, and this is my so called xi as a function of time, that is wave height. Now, what happened here? See, we will call this successive crest to trough, this as h, again here this to this as h. Like that, there is a number of pairs of h. See, each one, if you take crest to etc., then you end up getting number of heights. So, it is not a constant height. Now, you call that height, which itself is random nature. So, there will be, supposing I take a record for 1 hour, there will be so many h's occurring, h equal to like say this is 3 meter, 2 meter, 4 meter, 3.8 meter, etc., etc. Okay. This is what I can call height. Therefore, height is measured not amplitude, but height between crest to trough and trough to crest, between the two where the signal is just changed from minimum to maximum, each successive one. See, it is going up and then coming down and going up here to here. Now, let us say period. Now, there are two ways I can find period. One of the period would be if I take from crest to crest. See, this I take this as t. This this is one type of period. Crest to crest period. See, first of all, wave height, which is successive crest to trough, trough to crest, etc. Now period. Period is basically, as we saw yesterday, the interval between successive crest location, you may say, for a regular wave, that is here to here, the time taken for that is what we called period. And now this is same in regular wave case from here to here, any identical point if you take, the period is the repetition of that. But in here it is not so. So if I take peak to peak, I have got Tc, which we can call crest to crest period. But there is one more thing that is introduced, which is now called zero upcrossing period. See what happens, some of this crest to crest period, there can be a signal, I did not draw it, but say a signal can be like that. So here also you get crest to crest period. Okay. The other the period is what is called zero upcrossing. This is where the signal is crossing the zero in upward direction. You see there, here the signal is going from negative to positive. Excuse me. It is crossing the zero line in an upward direction. Okay, see this point A. A to the next one where it is crossing upward direction, this time interval. That is zero upcrossing period. When the signal is sorry, crossing the zero line in upward direction, from that to the next interval where the signal is crossing the upward period. This is called zero upcrossing period. So you can have, as far as period is concerned, crest to crest or zero upcrossing. Why I mean is that if you take a long signal, there will be again number of Tc, number of Tz, number of H. So you will have a long series of what is called a data file. I will just come to that in a kind of statistical thing in a minute. Now this is with respect to your period and height. Now supposing instead of period, I have the, see, I change that with respect to this side, instead of this thing, length. Then this side will become, instead of Tc, lambda c, and this will become, instead of Tz, lambda z. In other words, then you can call, you will have crest to crest distance to be one kind of length, or zero upcrossing to, and next zero upcrossing to be another kind of length. In other words, the concept is that as far as period is concerned, as far as length is concerned, you have got excuse me, I don't know what is, you have got two kind of definition. It can be measured from crest to crest, whether for period or for length, or it can be measured from the point where zero up crossing to the next zero up. This is called up crossing, not down, not this point. This is down crossing. Typically taken as up crossing to up crossing. Okay. Now let us say you took a signal, long signal. Now, so you have got now, let us say, long signal. You take it for a number of hours. Signal is here. So what happened? You are going to make a statistical analysis. You will now try to find out wave height, h, number of time it occurred. Now what it means? You have got a signal, so let us say 2 hour. You have got now, what is this happening? I don't know. one 1000 H values. Okay, you have got 1000 H values. H equal to 0.5 something, 0.25 something, 0.1, etc. Number. Now what happened? You have taken a statistics of H, but normally no H is repeating. We are having 2.35, 7, 2.912, 8.25. It is not convenient to do that. Instead of that, you can have an interval of H. Say you can have an interval of H 0 to 1 meter, 1 to 2 meter, 2 to 3 meter. So I can have H intervals, and then find out how many times the waves have occurred in that intervals. Otherwise, if you take each one, there will be 1000 different. You cannot have a plot. So let us say it has got some number, say 50 times. This has got some number, say 100 times. This has got some number 120 times. Like that you go. You have 8 to say 9. Say this is a 5 times. So now you have got total number n observation height. Okay. Now you can plot what is called a histogram. I can plot here what is called n here against the interval. So, this interval occurred so much, this occurred so much, like that. Now, this actually, this interval can also be written in terms of percentage. See, 50 signals out of n equal to, let us say, 1000. So, it will be, if I write in a percentage, 50 by 1000 percent, that is 5 by 100, 5%. Then this can be 10%, this is 12%, like that. I can draw here then probability, which is the percentage or the number itself. P is a better thing because P will tell me the number of the signal occurrence by the total number into 100. একটুখানি জল দিন, ঠিক আছে, actually for some reason so you see you can actually plot here what is called a probability distribution of the occurrence of wave heights, okay, in intervals. See, you could not do it. Now, this is typically known as a histogram. I will now come to that here. I will now come to that. Now, here what happened, next one. So, I have got here H interval, and here I have got number of occurrence. Then here I have got percentage of occurrence. This is some interval, say Hi. This is, say, number of occurrence Ni. This percent of become Ni by n into 100, when n equal to sigma Ni. See, what it happens is that I have a certain interval, say ith interval, say serial number, let me put. So, ith interval is for Hi, that means it is between, say, 5 meter to 6 meter, some interval. That number of times the waves within that interval occur is Ni, say 600. The total number that occurs is n, which is equal to sigma Ni. Naturally, this has occurred how many times of total? Ni by n times as a factor, and if you multiply with 100, it becomes a percentage. So, I can call this to be P in a percentage, or I can call this to be P of Hi, percentage occurrence of the wave height Hi. What is Hi? Hi can be the middle value of the interval. See, when I have an interval, I can take a middle value for plot, say 5 to 6 meter. So, I can write that as 5.5 meter. So, percentage of occurrence of waves 5.5 meter plus minus 0.5 meter would be Phi. Nothing but it is trying to tell us the percentage occurrence of certain waves. Now, you cannot hit an exact number, so we have to go in intervals. That is all I am trying to say. You can actually have small intervals. So, I can then plot that in an interval. I can say this H here. So, you see it occurred this much. Now this would be the, what we could do is that this area we can make it to be equal to the number Ni divided by n. Why we are doing that? I give an example. Many ways we can do that. So, supposing you do this way. Now, basically total area under that should be the total number of occurrence, divide by n, which means 1. I can make, if I call this to be P, this area should represent what is the occurrence of this wave height, the area. Therefore, basically what you are plotting is P, the values are P divided by delta H. You may say, if I call this to be delta H, okay. Why I am doing that? The reason is of doing that is that so that the area under that represents the total percentage of occurrence, which is equal to 1 in a probabilistic sense. It does not matter how do you do that, because we are not going to do this. It is only to show. See, if you look at this diagram, it is to tell you that, look, this wave occurs much more times than this wave. This wave occurs less times than this wave, and you can figure out the relative number of times of occurrence in a particular wave signal. So, this is nothing but the probability distribution of the wave heights in a given signal. Okay. Now, it turns out that if you keep doing that, this graph looks like, if you now draw a graph here, it looks more like this. I mean, in other words, it does not look equal, but it looks more like this. It looks more like this. If you do a histogram and if you make it small, what happens is that tomorrow I will draw it another one, this histogram part. Say I can make it smaller and smaller. I had initially interval taken as this. One person has taken this as interval, but I can make this even smaller intervals. I can take it at more. If I actually break the signal into much more number of small part, I get a, depending on how I have taken HI. See, if I, instead of taking number of occurrences of 1 to 2 meter, I say 1 to 1.5 meter, 1.5 to 2 meter, like that I can continue. So, I can actually keep refining this delta H, this I can make delta H tending to 0 a small. In fact, when delta H actually becomes 0, you will end up getting a continuous graph. In reality, it is not possible. It is like telling what is the number of occurrences of height between, say, 25.25 centimeter to 25.26 centimeter. Doesn't make sense. Normally, you will go in the interval of half a meter to 1 meter, not anything beyond that. Half a meter is okay. Even quarter meter is very rare. Now, my point is not that. My point is that having drawn this pH by H, there is a graph. It is called histogram, and this, or you can say probability distribution. Wave height. Similarly, you can do a same curve for period, same curve for wavelength, same curve for all the parameters that we measured. Normally, that is not what is done. Height is what is most important. Now, here there is a very interesting point. See, if I took the age of a number of students in the class, okay, you will find out that the distribution of that is normally what is called normal. That is, it has a mean and it is there is an equal chance both sides. This is what is called a normal curve. Sometimes one can you can call as a Gaussian distribution. It is a kind of distribution which is most normally occurring, and you will find in most places. As I said, like age of a student, etc., where the chances, there will be a mean value, say in a class age of a student 20, but there will be people less, people more. The chances of people less is more or less same as chances of people more, so it is equally spread. This is a bell shaped curve about a mean having both sides same, but the wave height curve turns out to be always something like this. It always tends to follow what is known as a Rayleigh distribution. That means it is chances of its occurring, I mean about the mean value, it is not symmetric, it actually tapers down like that. Okay. What it means? It basically means that chances of occurrence of heights very high are very, very low compared to chances of waves which are lower, and this makes perfect sense, why it should be so. This is why I wanted to discuss the physically. See, if there is the smallest wind possible, it is the wind which causes waves. Wind blows and that will excite a wave. Now, even if there is a small wind, say 5 knots, it is going to create waves, but what it will create? It will create the lower waves, waves of 1 meter, 2 meter, etc. Now, if there is a 20 knot wind, it will also create this 1 meter, 2 meter, but it will now create also some number of 10 meter waves. But it is 80 meter, also it will create 1, 2, 3, 4 meter going up. So, the lower ones are always occurring, no matter what the situation. Therefore, there is a tendency of lower, always having more. This is exactly why the chances that a wave of 2 meter will occur is always more than the chances that a wave of 10 meter will occur, because number of high ones occurrence, the phenomena that causes 10 meter will also cause 2 meter, but the one that causes 2 meter, exactly, therefore that is skewed. This is almost like I tell in my class that if you take a book, try to find out the number of digits 1, 2, 3, how many times it occurs. You will find the number of 1 occurrence is more than number of 2, and number of 2 is more than number of 3. If you just take, why? Because many chapters will start 1, 2, 3, 4 at ends at maybe 9 or 7. So 1, 2 are always occurring, the 12, 13. But on the other side, chances become kind of less and less. See, any number you start in a class or anywhere, say it goes to 57. So there is, see, if you see number of 6 occurs much less than 5 or 7 occurs like that. This is also like this, because 1 and 2 are occurring always, no matter how you start. Similarly, here lower heights are occurring always. So it becomes a Rayleigh distribution. So this is, it turns out that this is following a Rayleigh distribution. This is a very important property that we will find out later on. Now actually what happened theoretically, it turns out that if you have a distribution known, statistical distribution, Rayleigh, and if you can find out this, if you can fit this curve, you can actually find out all statistical property. For example, what is the chance that my wave is going to be more than certain height? That is the area under this curve. What is the chance that the wave will be not more than this but less than this? That is area under this. So if you actually have a statistical curve, you can figure out many statistical properties if you can actually fit this curve by means of some formula. Then you can tell what is the chance, look, what is my chance of wave height occurring at least once 10 meter. You can make it out, etc., etc. But this is a different thing. I will come to that later on. This is about the height. See, now a question comes, a very important question comes, a definition which is known as significant wave height. People would have or before significant, let me first write average wave height. Now you see, you have got now n number of HI values. That means you have said that this height occurs so many times, this height occurs so many times, this height occurs so many times, etc. If you simply average them, okay, then what you get is an average wave height. Just average of it is as simple as that. You have got, say, 0 to 1 meter occurring 100 times, 1 to 2 meter occurring 200 times, etc. So you take the mean value as 1, simply multiply the number of just take a geometric average. So you will tell that what is the average height. Okay, this is what is called average height. You can actually tell average height to be simply number of occurrence into HI divided by total number. That is the H average. The question is that most people use the word significant wave height more than average wave height, and so we have to know, because whenever you describe a sea, you will see here the term significant wave height, or some people will call 1/3 significant wave height. Okay, that is the most common thing. And what is the meaning of that 1/3 significant wave height? Now I will tell you that 1/3 H significant. In fact, people call it 1/3 wave height or significant wave height, both are same. Now by definition, this is the average of, now this is important here, average of highest 1/3 waves. Now this requires some description. Now you see, again I will go to that. There is an H here, there is an N here. So this H is 0 to 1 occurring say 20 times. This is 1 to 2 occurring say 60 times. This 2 to 3 occurring say 100 times. 3 to 4 occurring say 40 times, or okay, 4 to 5 occurring say 10 times. So 100. This 80, 180, 180 plus 50, 230, right? And say 5 to 6. I want to make it 240, that's why this is 10 times. So the total occurrence have become 240. So 240 records I have collected, of which 0 to 1 has happened 20 times, etc. Now what is 1/3? Now if you have to take a average wave height, I will simply have to multiply this. I have to take the h mean value, that is here maybe 0.5, here 1.5, 2.5, 3.5, 4.5, 5.5. I will multiply this with this and take an average. Okay, that is an average height. See, 0 to 1 meter is occurring because it can be 0.1. So we will take a mean value to be the representative height. Say 0.5 meter occur 20 times, 1.5 meters occur 60 times, like that I will tell. Then I will multiply and take an average. This is my average wave height. But 1/3 significant wave height would be that I have to take top highest 1/3 wave. Means what? I have got total 240 waves. I have to take 80 number of waves. Now 80 means this 10, 20, 20 plus 40 will become 60 and 20 from here. So 10, 10, 40 and 20 from here will make it total 80. So from this onwards I must take 1/3 of n number of occurrence of waves. That means as if the signal consists of only from here only 80 number of waves, but from here wherever 80 is hit. This is an important concept. See, here I have to take then the 10 number of this wave, 10 number of this wave, 40 number of this wave, and I have now left 20 because total has to be 80, so 20 number of these waves. So now if I take that part and then take a simple average of that waves, then what I get is called 1/3 significant wave height. In other words, it is average of the highest 1/3 number of waves, you can say, number of waves. This requires some sort of thinking that it is basically an average, but average of the top 1/3. So again in a spectrogram formula, see I have got this kind of formula here. This is probability of H, this is H occurring. Now the area under that is 1. That means total number of occurrence. Now I take this much of area, which is 1/3. That means these are the waves occurring, the top 1/3 wave. See, this area under that is 1 because it is normalized, the total number by number. That's how we have done it. So if you take 0.3, you take from this side a line where the area becomes 0.3. This area is 1/3. See, the probability of H by H, if you take the area under that full, it is equal to 1, because what it tells me is that some wave height must occur. It is 100% certain. Okay. So it's like if you take probability of a tail and head is half plus half, it is 1, because if you do, except in the movie, it is going to either be head or tail. It is not going to fall like that. Okay, it is going to be either head or tail. Similarly, here it means that there will be some height, whether 0.1 meter or 100 meter, whatever. So area under that is actually 1. But from this other side, this is the higher waves. You take a curve where the area is 1/3. Now this would represent the top 1/3 waves. Now you take this curve and take an average of that. This would be average of the highest 1/3 waves. Okay. Now you see, instead of 1/3, you can have 1/nth significant H, or you can say H1n. The definition is same. This would be average of the highest 1/nth number of waves. Suppose you want to find out what is 1/10 significant wave height, or H 1/10. It would imply in this diagram the top 24 waves average. If you say 1/100, then it will imply top 2.5 waves average, that will be 5.5. So you can actually end up getting from this side the top so much percentage of waves. See, if I want to do this, then this is area is 1/n. So if I take an average of that, I will get average of 1/nth wave height. So this is the concept of basically 1/10, 1/100th and 1/3 wave height. By default, significant wave height is referred to 1/3 wave height. See, when I normally, strict mathematician will say that, well, you must tell it is H 1/10 or H 100th or whatever. So the word is to use 1/10 significant wave height equal to H 110 or whatever, but normally we don't use the word that 1/nth. we simply use the word significant wave height. So, you see significant wave height by default means 1/3 you call that. So, somebody did not tell you the number 1/3, he just told you that look, significant wave height is 6 meter. You can safely assume that what he is referring is 1/3 significant wave height. Now, a question comes, you will ask why it is that 1/3 is very important, why not average, why are we not taking average wave height? You see, this is the question. Why the C people like to use, or whether people like to describe or use 1/3 average of 1/3 higher waves as a mechanism or a means of representing severity of the waves rather than average value. The answer is again simple. Answer is that if you take average, it tends to get pulled down because any small wave, any small wind will cause ripples. So, there are a number of small waves that are coming 1 meter, 2 meter, half meter, etc. So, if you take an average, you tend to get pulled down, and it does not appear to give you basically a sense of really severity of the waves, even in an average sense. Not only more, even in a even there is no storm, simple breeze, there will be small waves. So, small waves are so much there, like if you take a record, there is always small waves, they are trying to pull down the average. So, if I say average of 2 meter, it really do not indicate the severity of the wave. This is why average is felt not to be a number which kind of indicate to a person the severity of the waves, but 1/3 seems to be slightly higher than that, and therefore, it seems to be better. This is why a convention has it that people use 1/3 highest waves rather than average wave height. Okay, that main philosophy is that you don't want to take average because there are too many small numbers, kind of making it a bias on the lower side. But after all, you would like to have a higher estimate because your ship has to survive the weather. So, if you design it for surviving a kind of lower value, it may break up, whatever. So, you want to that, but you don't want to have it too much high. So, you want to have a kind of an average, slightly more than average. This is why 1/3 is used. Afterwards, we will find out that for our design wave, you have to design for things like H100 or for the wave height return period of 100 years, means what is the wave height that may come once in 100 years. That we will see later on, that extreme events for which your design must survive. Just like when you have done, say, our new Calcutta bridge, then you will have to find out what is the wind speed it must survive. So, there will be this similar term, it must survive a wind which may have a return period of 100 years, means once in 100 years there can be a storm with 200 knots. That is a different issue, we will come to that afterwards. Okay. Now, this is the concept of significant wave height. Now, the problem is that so far what we did, that we have found out from a wave this histogram of this thing, wave height occurring. But you see, we talked yesterday, if you look at the regular wave, you will find out that waves are not only decided by height, but also by length or frequency or period. These are interrelated to each other. Now, this distribution is not going to tell me this information. See, I can have another one for say period versus PT, but I can have two different sort of a histogram, but this does not tell us the relation between the H and the T. You see, this is independent. Here I am telling how many times this height has occurred, here I am telling how many times this length has occurred, but I am not anywhere telling what is that time a certain height of certain length has occurred. Because you see, after all, occurrence of say 10 meter wave, 1000 meter long, 10 meter high, 1000 meter long wave is very small slope, is much less severe than occurrence of 10 meter wave of 100 meter long wave. Because see, one would be occurring like this wave, another is occurring like this wave. See, if I just take height as a parameter, I do not know what the length is associated, then I do not really get a feel of the ocean, because I can have say 10-meter height, I can say that 10-meter occurred many times, fine, but the wavelength is 1 kilometer. So it looks still like that. No, histogram cannot give that other side. Because it can either give only height, it can give only period, but the relation between the two is not there. So it can, you see, supposing I give an example here, supposing you take the height, so there is a height like that, another signal with the same height but spread. Both of them, the heights are same, so you get the same H average, but obviously they are not similar waves, you see. Now if you take a length now, you get here longer length, but you don't know what is the associated height. So this H and lambda or T are not coupled in histogram, and you don't get a feel of that. And so we have to have another means of actually representing ocean waves, where information on both height and length are there together. This is a necessity now, because otherwise you do not understand what kind of wave. See, you want to know there are n number of waves of height 10 meters of length 100 meter, another 200 number of wave of height of 20 meter of length 200 meter. I mean, you want to have both together so that you can understand about the slope. That is what you want to know. You don't have it. Now before I go to that, you see, it turns out that if you take a random signal, you know, this is any random signal can be actually what is called analyzed by a mathematically by a Fourier series. You know, you can say, I will just write it first, then I will this thing. See, I mean, I just wrote some equation. What I wrote here, I will tell you. Now, random signal tells us, now xi t is a random signal. Now, this is xi t. Now, what I have done is that I have taken any random signal. You know, the height has been taken and it is obviously occurring. Now, there is a theory of signal processing that tells us that a random signal can be written as a sum of n number of harmonic or n number of sine curves. See, this is a what Fourier has said many years back, that any random signal can be broken down into n number of sine curves, or in other words, if you add n number of sine curves, you will end up getting a random waves, provided of course these curves have some kind of a random phase. This is why here what happened, this xi t can be expressed, this xi t is a random signal, can be expressed as a mean offset xi bar plus a sum of a n cos omega n t plus b n sin omega t. This a n and b n you don't know, some unknown sort of coefficients, but it is a sine curve and cos curves you can add. Why I write sin and cos here is that basically this is can be also written as cos omega n plus beta. You know, cos theta plus beta is, you know, sin theta plus cos theta, I mean, a sin theta plus b cos theta. Basically a signal with a phase can be written as sum of two signals. That is the idea, but this is only in going by mathematics. We need not worry about that. So what this Fourier theory says is that it is like this. If I give an example. If I take a sine curve of omega 1, another sine curve of omega 2, and another one of omega 3, you add these three together, what you will find? You will find something, some kind of random signal. So this is what the theory behind the Fourier analysis is, that any random signal can be broken down into a theoretically infinite number of sinusoidal signals, in practice some discrete number of sine signals. Okay, this is actually in terms of random process. See, in other words, conversely, if you can just check, if you take say sine, if you take 1 sine omega 1 t plus 1.2 sine say omega 2 t, some value, some t, you try to find out the behavior, you will find that it basically become random. and especially if you have a random phase between the two. You start this from here, next one you start from somewhere else here with a gap, another one from somewhere here. In fact, if you just add two sign with a random phase, you will find that it will look random. Conversely, therefore, any random signal can be broken down into n number of sine signals. This is what Fourier analysis says. This becomes a powerful tool, therefore, for our purpose here, because we have a random signal. Wave height that we have taken, this xi t, is a random. So, I can therefore break it down and tell that, look, this xi t can be thought of as if it is sum of n number of sine waves with some random phase, with some, they are waves having some phase which we do not know of. Okay. This is basically extremely an important event. So, the wave height that we got, therefore, can be expressed as if it is nothing but n number of waves I can write this in this fashion just by following Fourier analysis. This is actually, you can say, linear superposition. In other words, I can say that a random signal is linearly adding number of sine curves. See here, I am adding number of sine curves to get this. This is we are not going to the detailed mathematics, but it is, the concept is extremely important. So, I am repeating many times that a random signal, electrical, mechanical, whatever kind, it has actually come from signal processing in electrical engineering. When you take some record, now the signal comes, it can be random. Fourier actually tried to say that you can represent that as if it is sum of a number of sinusoidal waves with some phase gap between them, which you don't know. We don't know the amplitude of sine curves, you don't know the gap between them, but if you add number of sine curves, you will get that random signal. There is now a technique available that if you measure that, from there you can find out what are the sine curves that will cause this signal. You know, this is what is called Fourier transform and stuff like that, by which any random signal can be broken down to its constituent sine curves. Here again you may say, what are the sine curves? How do you choose n? It is actually up to us. Supposing I have a random signal, I want to say that, look, I want to break it down to 100 sine signals, then I will get 100 omega values and corresponding amplitude. If somebody says, no, I want to break it into 1000, you will get same 1000. It is a question of reverse breaking a signal. In other words, either those 1000 or those 100, if you add them, you will get that sine signal. So, in other words, you can, is something like this. See, 0 can be said 5 minus 5. You can also say 2 plus 3 minus 2 minus 3. You know, something like 0 can be broken down to 5 plus minus 5, okay, or 2 plus 3 plus minus 2 plus minus 3. It's up to you to break it down. You see, the breaking add gives you like this. So, same thing here. I have a random signal and I can break it down to number of components in such a way that when you add them up together, you get the signal back. This is what is called a what do you call a method of linear superposition, because you are linearly adding. Remember, linearly adding means you are adding 1 plus 2 plus 3, etc. Now, you see here, if you look at that, why it is so tantalizing, why it is so interesting, is because we have found out that regular waves are sine curves. Now, I take the signal and I break it into number of sine curves. Therefore, I can think that an irregular wave is nothing but sum of n number of regular waves. So, if I can add number of regular waves, I end up getting irregular wave. This is the most interesting part of the full phenomena, because we will find out even now next that the entire concept of how do we represent an irregular waves hinges on the fact that irregular wave is nothing but can be taken as sum of sine regular waves. This is exactly why we talked of regular waves, and we will find out that the complication will actually rest on finding out regular wave response, not irregular wave. Irregular wave will simply be sum of regular waves. You see, in other words, irregular appears very complex, but it is actually really very simple. It is nothing but just you break it down to some regular waves. That's all. If you can break it down, which will be a simple job, we will find out. That's it. is A plus B plus C plus D, that is all. So, it is this is a very interesting thing, but the question here comes, what is the logic behind that? The logic is, of course, you are actually adding sine waves. Now, how did we get sine wave yesterday? Based on linearity assumption. Sine wave was a result when the wave amplitude was small. So, this full theory of breaking down is obviously based on the fact that individual waves are of small amplitude. Individual waves are linear. If the individual waves are not linear, you could not have find out. But this turns out to be, the way that we will in next lecture I will come to the spectrum part of it. We will find out that the beauty of this is that even though we say the linear waves are added up, we will find out that the resulting wave can be nonlinear, can be steep. You see, now this I want to examine this linear superposition slightly more for this next 5 minutes or so. Now, you take one wave. See, you take one wave which is eta or xi, we are calling, xi equal to say 5 cos omega t plus say kx, within some certain amplitude, or let me call it with a1. Okay, a1. Now, another one, this is xi1, take as a2 cos omega t plus kx, same amplitude. That means I have a wave here like this, another wave here also like this, same frequency and different. This is my a1, this is my a2. What happen if I add them up together? What will be xi1 plus xi2? It is going to simply a1 plus a2 into cos omega t. So, it is going to be, if you add them up, it is simply going to be, where this is a1 plus a2. So, you see, if you take therefore exactly same wavelength wave, 1 meter wave, another 1 meter wave, you can add them up and say it is 2 meter wave. Now, conversely, supposing I find out that there is a 10 meter long wave, let us say I have a 10 meter long wave there, 10 meter high wave. I can think this 10 meter high wave is nothing but 10 number of 1 meter high waves added together. This is what is called breaking it up in pieces. This is only possible for linear waves. Now, you see what happens, this length is same. Now, I have another 10, so it becomes 20, then it has changed the steepness. So, you see, although the wave was steep, very steep, I can think that the steepness has come because I have added n number of linear waves. See, supposing let me give an example, this is 100 meter. Now, in 100 meter, a height of 10 meter is called quite steep, because by the time we will break. Now, suppose I have a 100 meter long wave, 10 meter high wave, 100 meter long wave. I can say that, look, it is nothing but sum of 10 number of 1 meter high waves. Now, 1 meter high wave, a 1 meter high wave is obviously small amplitude. It follows linear theory. Okay. So, now I am adding one linear wave, small amplitude wave, plus another one, plus another one, plus another one. The resultant wave I have got is actually not so small amplitude. So, in conversely, in this, when I break it down, it just turns out that even though sometimes the waves are of very high steepness, the principle of linear superposition or breaking them to linear waves also works somewhat well. So, it kind of is not too bad, You just cannot get this kind of wave, all right, but you can get high wave of this type by breaking it down, So, anyhow, so this is the principle of linear superposition. I will close this lecture now, and the next one we will talk about the more interesting part of how we can combine and how we actually represent a wave, irregular wave. Thank you. See, we are going to continue our talk on irregular sea waves. So, what we found out in the last lecture is that you can have, by Fourier analysis, a random wave signal represented as sum of n number of sinusoidal waves. See, this represents this side sum of n, basically here I wrote infinity, but we can make it n number of sine or regular linear waves. See, in other words, the random signal that we had could be thought or could be broken down into n number of sine curves, each of them representing a small amplitude regular wave with a random phase. This is my random phase with a this is my random phase. In other words, phase we have no information on. You are adding n number of waves, one is sin omega 1t, sin omega 2t, sin omega 3t, but the phase means the starting point is different. You know, one is starting from here, another may be starting from here, another may be starting from here, etc., etc. That is what decides the phase. So we can get that. We can get a random signal by synthesizing that into this. Now if you look at that, you will see here that this has got the amplitude part. Okay. This has also got the frequency part. See, k is after all connected to the omega, because k, you know, omega square is gk. Therefore, these and these are connected. So here you have got this. So I have got omega, I have got this. Both informations are embedded. Supposing therefore, if I took a random signal and if I could find out this and this together, then I will know for which omega what was my corresponding xi a. Earlier I got what is my height or amplitude, just number of amplitude, that is all. Again I had separately found out what are the number of omegas, or you can say period or length, but I did not know which wave had how many omegas. So, but in this one, if I did that, you see, I will find say, look, I have got in wave number 1 height so and so of omega 1 so and so, wave number 2 height so and so omega 2 and 2 so and so. So I have S omega, again omega. Now area under that curve, how do I represent area? See, there are number of way of representing area. Let me take this quantity, define moment. What is Mn? Now you see, tell me what is Mn. Mn represents the nth moment of this area, because see this, see, if there is a graph here, this is x here, this is y here, okay. Integration of y dx is the area under the graph. Integration of x into y dx will be moment of the graph about this line. Integration of x square into y dx would be second moment of area about the graph. Therefore, integration of this ordinate power into y dx, that is y, this ordinate power y to the power n into this dx, this d omega, represent nth moment of the curve. Okay. Why I say this nth moment of the curve? Because we will find out that many of the statistical parameters of this graph are related to that nth moment. Now you see, when you take n to be 0, that means if you take m0, what is m0? It is nothing but the area under the graph. m0 is nothing but the area under the graph, because m0 is s omega d omega. So m0 which is proportional to energy, which is proportional to height square. So the m0 becomes proportional to height square. Now we will come to that this in a minute. This is very important. See, this we must realize that obviously this is true, because what happens now, I took a spectrum, I synthesized that and I found out this graph, and I know now that the area under this graph is supposed to be proportional to the total energy of that random wave. That means if I took 1 square meter area and I kept on measuring the energy of content of that that surface, the energy would be equal to m0, that area under the graph. Okay, and that energy is obviously proportional to the average height square or some statistical height square, because more energy means there will be higher waves. Less energy means lower waves. They may not be 1 or 2, but there will be random waves. So average wave height or significant wave height would increase if there is more energy. So we will find out later on that this m0 is directly connected to various kind of wave heights. Okay, let me just concentrate right now on this part. Now it turns out, people, what people have done? People have actually been collecting data versus h1/3 versus t. So what happened? I want to find out what is my wave spectrum in C state 5. I will go back to the table and find out what is my h1/3 Tp. Then I go to the formula and I draw this graph. This becomes my spectrum for C state 3. See what happened? I go to this picture. I find out for C state 1 my h1/3 and Tp is so and so. I go and use that formula. It turns out that actually what happened? The spectrum, as wind blows, the diagram is not good. I should draw it just last and then quit. This, as the wind starts growing up, the spectrum actually begins to shift on this side. In other words, what happened? As h1/3 goes up, okay, as wind starts blowing more, your significant wave height will be more. You will end up seeing a spectrum which will having more number of long waves. This I will pick up on that little bit on the next class. Will be also more. So area. So you take two things: small height here and very high wave here. So the area under that is much smaller because obviously area under that is proportional to significant wave height, which is say 2 meter. But there will be more. See, when there is a 2 meter wave, it is all connected. I have got a wind blowing at 10 knots. 10 knots will give me number of small length wave, 50, 100 meter long wave with a smaller height. So average height is less. So the spectrum is shifted on higher frequency side, small wavelength side. As wind begins to blow more, I will have higher waves, also longer waves. So it will shift on this side and area will also become more. This will happen. This has a very significant effect on the ship motion, we will find out. See, small boats are operating in very moderate weather, but they are operating this small sea state. What happened when the typhoon starts to blow? You will have more number of 200 meter long wave or 300 meter long wave. Very long. You will, in one case you will have more number of small waves. Another case you will find much more number of longer waves. You see. So these are the two extremes, and we have to typically that happens. We will discuss more of that in next class. We'll stop today here. We'll do a little bit of this elementary spectrum part also in the next class.